This video is all about binomial distributions. Binomial distributions are not in themselves such a difficult concept, but I find it's one of the topics that trips a lot of people up early on in probability because they fail to recognize that what we're talking about is a binomial distribution. So I want you to keep that in mind. One of the keys to dealing with binomial distribution problems is realizing you're dealing with a binomial distribution problem. So it makes the definition very important. Let's take a look at the definition. You're dealing with a binomial distribution problem when you've got two possible outcomes. So that could be a heads or tails, a success or a failure, something or not something else. Obviously, when you've got two possible outcomes, the probabilities associated with each of those outcomes, they're complements of each other. So one's got a probability of p, and the other one's got a probability of 1 minus p. That encompasses the entire sample space of 100%. So there's two possible outcomes. There's some probabilities associated with each of those outcomes, and they're obviously complements of each other. That's not even really part of the definition. It's just that's the way it always is when you've only got two possible outcomes. And so you've got there's only three things you need to define in a binomial distribution problem. You've got a number of trials. There's a number of times you look for something, the number of attempts. The number of successes, and I put this in quotes because it's really not successes, it's just the number of times you see the thing that you're looking for. It could even be a failure. You could be testing a product, and the number of times you get a failure, you could call that a success. The key is that you have a probability associated with that specific outcome, and you're looking for that outcome. And you have a number of trials, you have a number of successes in all those trials, and then you've got a probability of your success, the outcome that you're looking for. So, for instance, well, we'll look at a number of examples, but this is the key. You say, okay, I'm doing something a bunch of times, I've only got two possible outcomes, and I want to know what the likelihood that I get a certain number of outcomes in all those attempts, or I get a range of outcomes in those attempts. These are all binomial distribution problems. We're going to look at a bunch of examples so you'll get a good feel for, okay, this is what we're talking about when we say binomial distribution problem. But just remember these three things. You got a number of attempts, how many were successful in those attempts. That's how you identify a binomial distribution problem. So we're looking for the probability of getting X successes in N attempts. Let's look at the first example. We have a class with 400 students. There are 220 women and 180 men. And you divide that class into study groups of 10 students each. What is the probability that a certain group will have exactly 4 men? So, what is our trial? How many trials do we have here? Well, we're talking about one specific study group. We're not talking about all the study groups. We're saying one specific study group. And all the study groups are 10 students each. So our number of trials here is 10. N is equal to 10. Actually, I'm going to do this in a different color because I think I'm going to use red later on. So let's go. N equals 10. What's our X? What's the number of successes? Well, in this case, don't get all angry at me, success is a man. I told you, it's not always success failure. And we have 4. We're saying, what's the probability of getting 4 men out of 10 students in that study group? And what's the probability that any given student is a man? Well, we have to go back to the original class size. And we have actually a class of 400, and 180 are men. So if we divide 180 by 400, we get 0.45 or 45%. So I'm not going to do the calculation at this point. Know this. We've identified this as a binomial probability-ish question. I'm going to show you actually 3 different tools for calculating the probability here. The question is, what is the probability that a certain group will have exactly 4 men? This is all the information we need. We've defined the number of trials, the number of successes, and the probability of a success. And so I'm going to move on to the next example, and we're going to come back and solve these later. In our second example, 5% of new products fail quality control testing. If you test 20 products, let's say you receive you're about to send a shipment out, and that contains a box of 20 of these products, what's the probability that none are going to fail quality control? So, let's think about this. Number of trials, well, we've got 20 products, right? So N. And I want you to think about this. When the reason people mess up in binomial distribution problems is they read a question like this, and they try to use one of the other techniques, some of which you haven't seen yet. and one of these other techniques for calculating probability, and they failed to identify this as a binomial distribution question. One thing I want to point out here is that binomial distribution problems frequently look like this. Oftentimes you might think, well, okay, I've got two possible outcomes, so that's A and B. Probability of A happening or probability of B happening. Very often, it's not like that. It's really the probability of A happening or probability of not A happening. So this would be something fails or it doesn't fail. And those are our two possible outcomes. So our N here is 20. We've got 20 products. That should be pretty straightforward. Our X here, what is our X? So we want to know what's the probability that none fail. So our X is 0. So we want to know, and notice here, is just like I was saying, success here, the thing that we're looking for is failure. So that's why success is sort of a funny term, but just it's easier to say than the thing that we're looking for happens. So in this case, we're actually looking for the probability that 0 fail our test. And what is the probability that any single one of them is going to fail the quality control testing? Well, we define that up here. It's 0.05. All right, next question. I've flipped a coin 10 times. What's the probability of getting at least 5 heads? Okay, this should start getting second nature to you. N here is 10. Oh, wait. What's the probability of getting at least 5 heads? Now, if we were saying exactly 5 heads, that would be x equals 5. But this is at least 5 heads. And by the way, this is another thing that trips a lot of people up. It seems simple, but you got to think about, like, what does at least mean? Or what does at most mean? And so if you have to just take a moment to think about what it means, at least means x is equal to 5, 6, 7, 8, 9, or 10. Any of those. What's the probability of getting any of those as our number of successes, in this case heads? And the p associated with a success, probability of getting a heads, is 0.5. I didn't give that to you in the question, but you know that because we're flipping coins. All right, let's do one more. In this example, we have a basketball player, and she makes 60% of her free throws, so she's not a tremendously good free throw shooter. At the end of the game, this player must shoot 6 free throws. We'll assume the other team is down, and they are going to start fouling this player. They're going to put her on the line, and they're hoping she doesn't make too many of her free throws so they can catch up. It's the hack-a-shack technique. So what's the probability? We're thinking about like the other team now. What's the probability that she makes less than 5 of her free throws? Okay, we're getting pretty good at this now. We say n is going to be equal to, she's shooting 6 total. It's kind of an ugly 6. And our x is going to be equal to, so what's the probability that she makes less than 5? So she's going to make 0, 1, 2, 3, or 4. And the p, the probability that she makes a free throw, is going to be equal to 0.6. All right, so I think we've done enough examples just looking at these binomial distribution problems and defining kind of what they are and what their key parameters are. Let's look at the first way you can solve these binomial distribution problems. Like I said, there's 3 ways I'm going to show you. So the first is to use this equation. I put it in red. It's the most important equation that we're going to be talking about here. It's this. It looks complicated. Don't be too intimidated by it. You can really just plug once you've defined the key parameters, you can really just plug in the numbers and it'll work. So it's the factorial of n divided by the factorial of x times the factorial of n minus x times p, the probability of getting x, to the x power times 1 minus p to the n minus x power. Ugh. Okay, so it's kind of a bear. This is why I'm showing it to you first. It's a little bit of a pain. This is to give you the probability of getting exactly x results, x successes, out of n attempts. So I'm going to copy this and bring it back to our first example. Here it is. Let's see if we can fit this somewhere. Ooh, I don't like where that is. Let's try over here. Oh, bother. Yay, okay, we got it. All right, so things are getting a little bit jumbled on the screen. But this is how we would set this up. And I'm going to use another color. And this is the only time I'm going to write this whole thing out. But you get 10 factorial over 4 factorial. And actually, I'm just going to simplify this a little bit. 10 factorial over 4 factorial times 6 factorial. That's n minus x, 10 minus 4, so 6 factorial, times 0.45 to the 4th power times 0.551 minus p to the 6th power. And if you do all these calculations, essentially you can simplify this. This ends up being like 210. Multiply the whole thing out. You get some value. I'm not going to do it on my calculator right now. You get a value of 24.84%. What does that tell us? That tells us the probability that a certain group will have exactly 4 men. It's 24.84%. Let's move on to our next example. Here's our equation again. In this one, remember, we were trying to figure out the probability. If the probability of failure in QC testing for any product is 5%, and we test 20, what's the probability we get exactly 0? This one's actually quite a lot easier to do. So I lied. I am going to write this one out. This is going to be 20 factorial over 0 factorial, also known as 1 times 20 factorial equals 0.05 to the 0th power, also known as 1 again. Wait, why did I say equals? Not what I wanted. Times, all right, and times 0.95, that's 1 minus p to the 20th power. All of this simplifies really easy. That simplifies out to 1. 0.05 to the 0th power also simplifies out to 1, so we have 1 times 0.95 to the 20th power, and that is equal to 35.85%. All right, moving on to our third example. Now, I didn't actually calculate out the equations on example 1 and example 2, or rather I did it previously, but it actually, it takes a second. You have to set up the whole equation, you have to plug it into your calculator or Excel, and it'll take you a minute or two. It gets really tedious when you start having a range of values that you're looking for. So in this question, remember, we were looking for not just the probability of getting exactly a number, but the probability of getting several, essentially a range. So this is saying, what's the probability of getting at least 5 heads? So we said, okay, so x is going to be equal to 5, 6, 7, 8, 9, 10. Well, what we could do is we could set up this equation here and do it for 5, and then do another one for x equals 6, and another one for x equals 7, and 8, 9, 10, add them all up, and that would give us the right answer, but it would be tedious for sure. So now I'm going to introduce you to our second technique. Our second technique for calculating binomial probabilities is when we're dealing with a range, it might be more useful to go to a binomial distribution table. And let me show you how this works. All right. On our left side over here, it's given us the n. That's the number of trials that we're looking for. Next to that is the number of successes out of those trials. And along the top, we have probabilities. Now, notice this is somewhat limited. I've only got a certain number of defined trials here, a certain number of defined successes. Well, okay, no, they've covered every possible success within those number of trials. But the trials, they have to be a multiple of 5 in order to use this particular table. And as this is also true of our probabilities. They don't give us all possible probabilities. So, to do so, to make a comprehensive binomial distribution table, it would be massive. So this is good in certain instances. What does it tell us in here? This is the real key. What is this? This is a cumulative probability distribution. Now, hopefully you all remember what that means, but I'm going to tell you again anyhow. It means what the values that you're getting here are the probability that you get a certain value or less. Let me remind you what that means. So if we have 10 trials and we're looking for the probability of getting 6 or less, and the p is equal to 0.2, so the probability of getting a 2 or, I'm sorry, the probability of getting a success is 0.2. So the probability of getting a 6 or less is 0.999. I hope that makes sense to everybody. All right, so let's you know, or let me just give you one more example. So let's say we had 5 trials, and the probability of getting success on any one trial is 0.40. What's the probability of getting 1 or less? Well, we look down here for x equals 1. 0.4 is our probability of getting any one success, and it's going to be 0.337. So this is the probability of getting a 1 or a 0. That's why we're always seeing 100% probability at the full number of trials, because this is the probability of getting that number or less. So think about our example here. We had, let's actually go back to the example here, example 3. We're flipping a coin 10 times. What's the probability of getting at least 5 heads? So we want to know the probability of getting 5, 6, 7, 8, 9, or 10. So it's pretty obvious the probability of getting, going back to our probability distribution table, it's obvious that the probability of getting 10 or less is always, I mean, that encompasses the entire sample space. So that's always going to be 1. We don't really need to look it up, but I've gone ahead and done it anyways. And now let's think about where we have to go from here. This is going to give us all the probabilities of getting a certain number or less. And what we want is the probability of getting a 5, 6, 7, 8, 9, or 10. So what we could do is take the probability of getting 10 or less and subtract the probability of getting 4 or less. All right? Because that's going to leave us with just the probability of getting 5, 6, 7, 8, 9, or 10. It's everything but the probability of getting a 4, 3, 2, 1, or 0. So here we're in the right place. Our n is equal to 10. Our p is equal to 0.5. So we're saying the probability of 10 or less minus the probability of 4 or less. So that's 1 minus 0.377. And that's going to be equal to 0.6 something something. I should be able to do this in my head. 2, 3. But I didn't. All right. Let's actually, let's use the binomial distribution table for one of our previous examples. Let's say, let's go back to example number 1. Let's use the binomial distribution table. So here we had our n is 10. We're going to be able to use the exact same table. Our x is equal to 4, and our p is equal to 0.45. Now, like I said, the binomial distribution table gives us cumulative, I'm in the wrong place, gives us cumulative distributions. So we can't just go, okay, our x is 4, and our p is 0.45, and our n is 10. That's not going to work, because it's going to give us the cumulative. It's going to say this is the probability of getting 0, 1, 2, 3, or 4. We want to know just the probability of getting 4. Any ideas how to do that? I bet most of you have figured this out already. It's the probability of getting 4, which is 4 or less, sorry, 0.504, minus the probability of getting 3 or less. And that's just going to leave us with only the probability of getting 4. So that's going to be equal to 0.504 minus 0.266. This is going to be 38. It's going to be 23. 0.8%. I suspect that isn't correct, or at least these two numbers don't match because I did a calculation wrong in the first place. So for those of you who were following along originally and got a number that was different, got 23.84%, I apologize. I hope there wasn't too much confusion. Tell you what we will do is we'll use our third technique on calculating binomial probabilities when I introduce that, and we'll come back and see which one's right. I highly suspect that I messed up this complicated calculation and that the number from the table is in fact correct. So another reason to try to use the table or the third method whenever possible. All right, let's take a look now at our fourth example. So this is the example where we have the basketball player shooting free throws. And the tricky thing here, so just to recap, we have a basketball player, she's shooting 6 free throws and she's got a 60% chance to make any single one of them. We're asking what's the probability that she makes less than 5. The trick here is going back to our table. We've got this table that lists 5 trials, 10 trials, 15 trials. I've even got one that lists 20 and 25 trials. But here we've only got 6. We don't have a table that is just going to list 6 trials. So what are our possibilities here? Well, we could go back to this equation here and do this for 0, 1, 2, 3, and 4 for x. Make those calculations. But as you saw already, it's, there's possibilities of errors just because it's kind of a complicated equation. You have to do that 5 different times. One shortcut that we could take, which would shorten things up, I think, considerably, is to say, asking what the probability that she makes less than 5 is sort of like asking, it's the complement of saying, what's the probability that she makes 5 or 6? This probability that she makes less than 5 is equal to 1 minus probability of x equals 5 or 6. Does that make sense? We're essentially saying we could just do the calculation for x is equal to 5, add that to the probability that x is equal to 6, and then subtract that from 1. And that's going to give us the exact same thing. These are complements of each other. X is equal to 0, 1, 2, 3, 4. 0, 1, 2, or 3, or 4, which is the same thing as 1 minus the probability that x is equal to 5 or 6. So that's one thing we could do. But instead of doing that, because we'd still have to run this equation twice for x equals 5 and x equals 6, and then subtract that from 1, I'm going to show you the third way that we can do these calculations. And that is using Excel. And Excel makes it really easy. So what we do is we start to enter in this function called binomial. I always just use the same function, binomial distribution range. And down here, you may not be able to read it. It asks for trials, the probability of success, a number, the lower end of our range that we want, and the higher end of our range that we want. So in this case, I'm going to say our trials are 6. Probability of success is 0.6. That's the percentage of free throws she typically makes. And the lower end of our range is going to be 0, and the upper end of our range is going to be equal to 4. This is an inclusive range. So we're saying, what's the probability that she makes less than 5? This is the probability that she makes between 0 and 4 free throws. And the answer is 76.67%. Let's go back and use this exact same equation on our first example. Example 1, we had trials, we had 10 trials. We were looking for the exact value, the probability of getting exactly 4, and the probability of success on any specific trial was 0.45. So let's go back into Excel and enter that in. I'm going to say equals binomial distribution range. Our n is 10. Our probability is 0.45. Our lower end of the range is 4, and our upper end of the range is also 4. Because we just want to know exactly the probability of getting exactly 4. And so that is equal to 23.84 Going back, that was the result that we got from using the table. I just keyed this in wrong or entered it in wrong. I don't know. Probably I got the right result and just copied it down wrong. So the correct answer is 23.8. And that is verified by Excel. 23. This is bothering me. In fact, let's make these into percentages. There, that looks much nicer. All right, let's do one final example that we haven't seen yet. Example number 5. An MBA program tries to have an incoming class. They're shooting for an incoming class of 350 students. And they know, historically, that 70% of their admitted students will enroll. So they admit somebody, there's a 70% chance they're going to enroll. Question number 1. How many applicants should the program accept? Now, I made this a little bit difficult on you because I really didn't get into this on the previous screen. But I wanted to show you, first of all, the binomial calculation. There's a couple of other important points here. First of all, the expected value when we're dealing with a binomial distribution is just going to be n times p, the number of trials times the success. This should sort of make intuitive sense to you. And I think that going back, when we look at this next example, you'll see that really it's very intuitive. And then we have an equation for variance. I would recommend copying down all 3 of these equations. Standard deviation is always just the square root of variance, so that shouldn't be any more difficult to remember in itself. But remembering this, expected value is just going to be the number of trials you have times the probability of success on any one specific trial. So, thinking about that, how many applicants should the program accept? Let's put this up here. Well, we know 70% of them enroll. We want 350. So if the expected value is n times p, well, we just have to figure out what n is. We're saying n times p, we want it to be equal to 350. And we know that p is going to be equal to 0.7, because that's our acceptance rate. So n equals times 0.7 equals 350. So n is going to be equal to 350 divided by 0.7, and that is going to be equal to something. 350 divided by 0.7 is 500. Oh. That works out nicely. All right. Second question. If the program accepts 500 applicants, there's a little bit of a giveaway on the previous question. If the program does accept 500 applicants, because they think that's going to give us our expected value of 350, if the program accepts 500 applicants, what is the probability that the program gets, they actually net, between 330 and 370 students? Now, let's think about the 3 ways we could calculate this. So we're saying our n is going to be 500. The p, we'll start with p here, is going to be equal to 0.7. And the x is between inclusive. Okay, let's, I'm going to define this as inclusive, because I didn't do that in the question. You might read this as 331 and 331 and 369, but I'm going to call it inclusive. Between 330 and 370 inclusive. A couple things we could do. 3 things we could do. Number 1, we could start by going to this equation. And we could perform this equation for every value of x between 330 and 370, and that would take us the better part of a day. Number 2, we could find a binomial distribution table, and that has an n of 500. Good luck. And we could look at the value for x of 370, and that would and a p of 0.7, which, okay, you might actually find one with a p of 0.7. Unlikely you'll find one with an n of 500, and it would be a really big table. And then you go down to x is equal to 370, and that's going to give you the value, the probability that you would get 370 or less acceptances, and you'd subtract from that value the probability that you would get 330 or less acceptances. So you'd have to go up, look the value up for 370, and then subtract that from the value for 330, because remember, those are cumulative probability distributions that you're seeing in here. Now, I'm going to guess that you won't find that table because it would be a really big table, so we'll have to go to Excel. Use the same format that I've been using. I'm going to go into equals binom dist range. Number of trials is 500. Our p is 0.7. The lower end of our range is 330, and the upper end of our range is 370. And that's going to give us a probability of 95.5, meaning if the number of students we really can deal with is between 330 and 370, based on our acceptance rate and admitting 500 students, we can be 95% sure, a little bit better than 95% sure, that we're going to get in somewhere in our sweet spot of acceptances, so between 330 and 370 acceptances. Thanks for bearing with me. I know this is a lot of examples of binomial distribution. Like I said at the very beginning of this video, the real key is recognizing a binomial distribution problem when you've got it. And then whether you use Excel, whether you use the equation, or whether you use a binomial distribution table, I don't really care. I think that it's a pretty easy, they're all fairly straightforward. I know I made a mistake, but they're all fairly straightforward in terms of execution. You do have to remember the binomial distribution table deals with cumulative distributions, and so when you look a value up, it's that number or less. But the real key is just reading that problem and saying, okay, I've got two possible outcomes. I'm looking at a certain number of trials, a certain number of attempts, and I want to know either the probability of getting exactly a certain number of values in all those attempts or a range of values in those attempts. But that's the real key, is you're dealing with two possible outcomes, a certain number of attempts.